Hello students and welcome to this course on computation theory. My name is Hugo Bergier. I'm an assistant professor at Regis University in the computer science department. I've been there for 2 years. I come from France, so that explains my accent. My background is in applied mathematics, but I also studied mathematical logic and the most theoretical aspects of computer science for my PhD, so that's why I teach those courses. I also work for a startup, Phase Change Software, located in Golden, that does program analysis. I work as part of the R&D team, but also do some concrete software development and coding. So I have a foot in the concrete stuff and in the industry. That's a good combo with Regis. With the research and teaching. So that's my background, my research interests are around a lot of things that we're actually going to do in this course. Theoretical computer science, lambda calculus, logic, all these kind of things. I wanted to talk to you a little bit about this course, what we're going to do together. This course really is asking the question, what is computation and what is computable? And we'll see that these two questions are actually very related, because the problem is that we try to define computation formally with, precisely, not just in a vague way. Quickly we ask, well, once we have a model that defines computation, what can we compute with it? We can do this, we can do that. And we'll see different models to see, well, what can we concretely compute with this model or this model or this model. So quickly, from the question of how could we define computation comes the question, well, what can we do with that? What can we concretely achieve? Because as you know, computation, computer science is a science of doing operations, of doing things. It's not just pure theory. It's about going from point A to point B and actually computing something, getting some output. So we cannot separate the theory of what is computation to the actual doing. What can you do with it? What can you compute with it? So we'll look at that. We'll look at different models and we'll see, okay, with this model we can compute that, but with this model we can compute more, and this model even more, okay? But if we take from this other perspective, we can directly compute this like larger bubble. So we'll look at that, and this is kind of like how history worked in the 30s, 40s, 50s, when the first models of computations came out. And we'll kind of go through that process to realize, oh, that's interesting. Whatever we take, whatever angle we take, whatever model we pick, and we'll see three big models, the main ones, which are Turing machines, lambda calculus, and recursive functions. Whatever model we pick, we reach the same conclusion, the same space of, the same realm of the computable, of things that we can compute. And they are equivalent. And therefore, this defines computation. You see how we need to reach first this conclusion to be able to say, well, that's actually a good definition of computation, because whatever angle we take, we reach the same conclusion, we reach the same space of the space of the computable. Okay, so that's kind of how we're going to take it. We're going to start with the Turing machine approach, because that's the one that is the most intuitive for a computer scientist like you guys. That's how you think. You think more in terms of Turing machine, okay? But the two other ones, we're still going to see them because they help us, again, reach that conclusion, that unity. Otherwise, we would not be completely so sure about our result. So to really give you this conviction that, okay, that's really the largest space of what is computable we can reach. We'll see these three models. These two other models are maybe less intuitive, but remarkably efficient and actually very simple when you think about it. And they are also tied to programming languages you have seen, like Haskell, for instance, that you have studied in a previous course. this is very, very close to lambda calculus, as we'll see. So we'll look at these first Turing machines, then the two other models of computation, and then we'll bring them together to compare them to see, okay, how they compare in terms of what is computable, okay? And then once we have that, we'll look also at beyond that. Okay, so if we have this space, what is outside of this space? What is not computable? And what about hypercomputation? Okay, so we'll look at these kind of things, and we'll finish with the problem of theory of complexity, which this time looks only at within the bubble, if I may say, of the computable, but then makes a distinction between what is actually really reasonably computable for the lifetime of a human being and what is not. Okay, so we'll look into what we call intractable problems and things we just could theoretically compute but practically cannot. Okay, so there is a practical component to this course. Now, it's not a practical component in the sense like we're going to teach you how to do better programming or to code better or anything like that, okay? So in this sense, this course is going to be radically different from any other course you have had before, where at some point in any other course you had before in your curriculum, there were some aspect of teaching you how to do things, how to program, teaching you a new language, teaching you how to build efficient algorithms or things like that. There is nothing about that in this course, and you have to really understand that, okay? There is no aspect of this course that is going to help you be, in some sense, a better programmer, or to practice your job in a better way, because these are foundational topics. But nevertheless, I think it might be the most important course of your curriculum and the more useful even. And I'm going to try to explain to you why. I think it's important as an introduction to really talk about that. There are several reasons. First, it's a frame of mind. We're gonna look at things in a very formal way, in a very strict way, which can really help you as a computer scientist, because you're not dealing with languages like English or French that are very fuzzy and ambiguous. You have to deal with very exact things. And we're going to look at very exact results. This is a very formal discipline we're going to enter into. Formal means there is no room for ambiguity. It's very rigorous. There is no room for different interpretation. It's an exact science. And that frame of mind can be really a good thing for the training of your way of thinking, the training of your mind for the future. I think it's this sense of rigor for terminology. You know, when we talk about certain terms, when we say decidable, when we say Turing computable, Turing recognizable, we mean certain things. What do we mean exactly? Okay, we have to be very, very precise, and this precision, this kind of discipline of the mind is something very useful, I think. Another aspect that is maybe not as compelling, but I find very interesting, is more on the side of aesthetics. All the models we're going to see are a different way of framing things, and they lead to the same conclusion. There's some kind of harmony in this course, and I hope you're going to see it at some point. Some kind of harmony between different models, where they approach things from very different angles, very different way, but somehow they are equivalent. It's like building bridges and connections between models, between different systems. So this whole like systemic approach and how things in the end harmonize, even when you take very different approaches on one topic, you have kind of this, it's like, you know, the computable is at the center, and you have this whole like sphere around it, and everything is reaching toward the same conclusion. That's kind of harmony. It's just pleasing to study and to see, and reassuring too, right? We know, okay, there's something that just makes sense as a whole here. Now, on the more like practical side, another thing I wanted to mention is that a lot of things you're seeing in your curriculum are going to be incredibly useful for your job. Like, you're going to get out of here and you're going to apply it immediately, and it's going to have a tremendous use compared to what you're going to see in this course. I'm going to be straightforward with you. I'm talking about your first job, maybe your second job, or maybe in the next 5 or 10 years. But the thing is that things are evolving so quickly in our field. Technologies are changing radically so fast that there's no guarantee that the mobile course is going to be still valid in 10 years from now. It's likely not going to be. This course is. This course will always be. That's something also reassuring. It's so foundational. There's nothing that we're going to study together that can become obsolete. You have to understand, and I'm going to stress that many times, and I won't stress it enough. Nothing you're going to see can become obsolete. Can you imagine that? I mean, the result we are going to look at throughout this course are going to be valid 5 years, 10 years, 100 years from now. They don't change, okay? They are permanent results because they are mathematical in some sense, okay? So that's something you have to understand. There is something about this course that you can hang on to, and that can be some kind of foundational building block for all your career, and can serve you for a very long time. So that's another aspect. Now, there are some aspects of what we're going to see that have actually concrete practical implication and can be incredibly useful for your career and your job and your activity. I'm going to just give you an example. My company, the company I work for, in the industry, we do code analysis, we do program analysis, and we try to somehow help developers understand very large pieces of code very quickly, even though they don't know anything about it. So we kind of read the code for them, okay? One of the things we'd like to be able to do in this process, in this invention, is to be able to take two functions and say, well, these two functions are actually doing exactly the same thing, right? They look different, they have different code, but the behavior is exactly the same. You put two inputs, they will always return the exact same outputs. Okay, that would be incredibly useful. Now we're going to see a result during this course that says we can do that, okay? Actually, we're gonna even see that it's not just that we cannot compute that we cannot even build a Turing machine or program that could potentially do that, right? It's actually one of the things beyond the space of the computable. It's outside. It's actually even outside the space of the recognizable. We'll see that later. So it's actually really useful. Rather than wasting your time trying to find an algorithm, how can I find an algorithm where I can feed it to any functions, any language, and it's gonna return me if they are equivalent or no? Rather than wasting your time doing that, you already know you can't, because there is a result that says you can't. It's impossible to write such function, such program, okay? So it's actually very concrete. So we can find other ways, okay? We can find some way around it to still get some kind of hints or maybe indicia of similarities between the two functions or things like that. But we can do that in the absolute. So there are some concrete results we're gonna see here that are very, very useful in some areas of software development. Okay, so that was my spiel for why it's still a useful course. I hope you're going to enjoy this course as much as I enjoy this topic, and I wish you a very good term.